In this lesson, we are going to be learning how to create an end-to-end deep learning classifier for raw samples. We will be using Keras and TensorFlow, so make sure to install those. So just like in the lesson on n-grams, we are going to be reading in pure byte sequence of our samples. We will be thinking of this byte sequence as a series akin to a video or audio stream, and then our neural network is going to classify it as one of 9 types of malware. First step will be to embed the byte. As always, we want to convert our input into a numerical form. For that reason, we are going to embed each byte into an 8-dimensional vector. This part is called embedding when you take your data and you vectorize it. There are various types of embeddings ranging from sophisticated like word2vec, or ones you specifically train for your own classifier, a more simple one like the one I will show. In our case, what I'm going to do is take each of these bytes, represent it in binary form, and when I see a 1, I will put a 1/16 in that index of my vector, and when I see a 0, I'll put a negative 1/16. Like I mentioned, there are much more sophisticated methods, but the literature has shown that for this specific problem, it suffices to do this simple embedding. Next, we are going to read in our samples, and I'm going to set an upper limit on the number of bytes that I'll be reading per sample. The reason for this is that we might have some computational constraints. For instance, I'm using my laptop, which does not have much computational power. And also, we want to have all of our samples be of uniform size. So we're going to read in 15,000 bytes per sample. Each byte will then be embedded, and all of this will be collected into our training X set. We'll also want to record the label, which is available in the dataset. And once we are finished with this process, going over all the files, we'll have our training dataset. We will want to convert our labels into a categorical form from 0 to 8, because that will be how our neural network will accept it as a target. Finally, we're going to create our neural network. So let's work through this one step at a time. First, I'll declare my optimizer. I found that stochastic gradient descent with these parameters works quite well for me. Then I'm going to be using the Keras functional API. If you look at the layers, you'll see that they look like a function. conv1d with some parameters takes in inputs and then gives you an output, conv1. And same thing for conv2. And activation takes in conv2 and gives you an output. In other words, just like a function. And the advantage of this functional API over the regular way of writing Keras lines is that it gives you much more flexibility. You can take the outputs of one layer and feed it in later and then backwards, and you can do all sorts of combinations of your outputs and inputs, which you otherwise cannot. So first I'm going to specify the shape of the input, which we said 8, max size. 8 because each of my embedding vectors is of dimension 8, and max size because that's how long it is. And if it happens and my file is too short for max size, then I will simply pad. Next, we're going to take this input and we're going to feed it into a convolution here, and again I'm going to feed it into a convolution the same way here. I'm going to activate just one of these convolutions here, the sigmoid, but not the other. And then I'm going to multiply the two of them, the activated version, the non-activated one. This is one instance where you can do something relatively creative by taking the inputs and convolving them and then combining the outputs of different layers. And then I'm going to activate the result of this multiplication, going to global max pool, and then I'll have a dense layer and eventually the final layer for prediction. To summarize, we embed, we convolve in parallel, we activate one of the convolutions and multiply by the other, then we max pool, and finally we use a dense layer to make a prediction. Compile our model, we have a summary, and next I'm going to start training. I take in one batch at a time, train my model, and finally I'm going to predict on the training set just to see how the fit is. And the predictions look like this. They're a bunch of numbers, which we can think of as unnormalized probabilities. Consequently, the highest number per row per vector corresponds to the most likely label. I can then read in each of these rows, pick the largest one, and I'll have my predictions. So prediction 2, 1, 8, and so on. And I'll compare it with my actual labels, and it gets about 89%. Pretty good for our first iteration, especially considering that there are 9 labels. Then we're going to do the same thing with a testing set. And again, I'm going to get my accuracy, which is 86 now, which is slightly below the training one, but not by much, which suggests that there isn't much overfit. In a production environment, my next step would be to figure out the correct tuning, to increase the data size, to play around with the architecture, to think about my class balance, and to think about whether I want to give each mistake the same weight in terms of error, or whether I want to weigh one type of error higher than the others. The technique I've just shown you of taking in raw samples into a deep neural network is really on the cutting edge of the field, and you now know how to do it.